Sauce here. This is a video lesson on using U substitution for integration. U substitution can be used for trigonometry and algebra. It's simply the strategy of choosing a letter, traditionally U, to represent a more complicated expression so that what you're working with is temporarily simplified and easier to deal with. Integration is challenging, so using U substitution is a very common strategy. Taking a look at this integral, you may be asked to find the antiderivative of 7x squared plus 1 all to the fourth times 14x. One perfectly acceptable way to integrate is to guess and check. We might guess that because this 14x may be observed to be the derivative of 7x squared plus 1, that the guess of the antiderivative would be the 7x squared plus 1, but we would raise this exponential value to 5. We expect when we integrate a power, we raise the exponential value by 1. And then we would check our guess with the understanding that if I take the derivative of this and it recreates what I had integrated or need to integrate, then my guess must be correct. And in taking the derivative of this, we are going to use the power rule for this composite function, bring it down in front, multiply by what is composing the fifth power function, lower the exponent by 1, and then chain rule by multiplying by the derivative of this inside, which is 14x. So my strategy of guessing was informed by knowing that when I would check, I would produce the 14x outside that I saw initially. But there is an extra 5, so I can modify my guess by multiplying by the constant 1/5. So if I checked this, then the 5 that would come out in front using the power rule for a derivative would cancel out the 1/5 that I placed there and disappear from my check. So it recreated the original expression that I wanted to integrate. This guess now has been modified and is correct because it checks, so I'll add the plus c for the constant of integration, and I have found my antiderivative. But the process of guessing and checking feels like to some kind of clunky and not authentic or not entirely under your control to get it right. So we can use U substitution for a more reliable process. We're going to use U substitution and confirm the integral that we already know the answer of. U substitution goes like this. We use U to represent an expression. In this case, it will be the expression 7x squared plus 1. If I replace this expression with U, it will certainly simplify what I need to integrate. But I'm not ready to do that because if I reconstruct the integral by substituting U in for just this, I'm still going to have a power of 4, and I'm still going to have a 14x, and it will still be with respects to x. So there's more that I need to do than just put my substitution of U in. I'm going to take the derivative of U with respects to x. When I do, it becomes 14x plus 0, so we won't show the plus 0. Now I can substitute the 7x squared plus 1 by putting U in for it. I now have this 14x that can be substituted with the du dx. But I'm going to modify this one step further by separating this notation for the derivative. I'm thinking of this as a fraction now, and I'm going to multiply both sides by dx. When I do, I get du by itself, and on the other side, I have 14x times dx, or I can think of it like I'm multiplying by the dx. Now I've got the pieces that when I substitute in, I will recreate the integral, but there will no longer be any x represented in it. It'll be entirely in terms of u. So I'm going to recreate the integral. I'm going to substitute u in for the 7x squared plus 1. It's still to the 4th power. And the entirety of the 14x dx will be substituted with du. When I've made these substitutions, the integral that I have created here is quite easy to integrate. It's simply a power rule for integration, so I get u, raise the exponent, divide by the new exponent, plus c. But I don't want to express my answer in terms of u. I have to resubstitute what I've decided u to be. So for my final step, we get 7x squared plus 1, that's resubstituting in u, for u, to the 5th power. I'm dividing by 5. I'll represent it as the fraction 1/5, and I can't forget c. I've recreated, now by a reliable process, what I expected and got previously by guess and check. Let's see this process again. I have an integral, the sine of x squared times 2x with respects to x. And again, I can see, possibly, if I've done lots of integration, that the 2x is the derivative of x squared. So I might be able to guess as to the antiderivative of this. But many are not so familiar or can see that that's going to happen and then guess efficiently so that we can get the answer quickly that way. The reliable process is to choose an expression for u to substitute. And the expression for u, though you have some choice, is often going to work out, and u substitution doesn't always work, but there's a chance that it's going to work if your guess is the more complicated or the higher exponential expression. In this case, I'm going to set u as equal to x squared because part of the process will always be the need to differentiate u or take the derivative u with respects to x, which will lower the exponential value, which means that your original choice for u ought to be the piece that has the higher exponential value. I'm going to do what I did before and separate this notation so I get the du by itself is equal to 2x times dx. I'm going to try to rebuild the integral. I'm going to integrate. Sine is not a part of what I'm substituting. It still remains. But now I'm taking the sine of u, as I'm substituting u in for the x squared. And the 2x dx that remains, I can substitute du for. So my attempt to reconstruct the integral worked since there is no representation of x left, and it's entirely in terms of u. This is also a very simple antiderivative to find. It is negative cosine of u plus c. But we want to resubstitute what u is equal to, and my u is replaced with the x squared. Don't forget c. U substitution can help. It doesn't always work. So we have many techniques for integration. U substitution sometimes takes quite a bit of work, but not as much as integration by parts, a tool for integration that we'll learn in the future that can be very lengthy. So if U substitution looks like it might work, it's usually worth trying it until you see something else is going to help you, or you can finish integrating.